Okay. Hello. I'm Mark Schwederman, and I'm going to talk to you tonight about flexible array members in Swift. And if you have no idea what those are, don't feel bad because I didn't either until a few weeks ago. Is anyone here using Swift currently? Are you calling into lower level C APIs with Swift? And are you already also relatively comfortable with those lower level C APIs? Okay, well, hopefully there will be some stuff here for you then. The last time I used C in anger was probably in college. So I literally spent like 3 days getting my head around how pointers worked again the other week, which is really embarrassing because I thought I already understood that from using Objective-C recently. But anyways, I'm going to tell you a little bit about a problem that I ran into working with Core Audio and how one would use this code in Objective-C, and then show you how you can do it in Swift. Core Audio has lots of structs that look kind of like this, and this is the simplest one I could find. Lots of them are huge and gigantic and have substructs and all kinds of other things. If it's not clear, the top is C and the bottom is the Swift version of that. Usually dealing with these things in Swift is pretty easy. You can just instantiate them like normal objects. Most of them have default initializers or ones where you can pass in the properties. That generally works pretty well. The one where I had a problem though was one that looked like this. Creating was fine, assigning to the simple typeset was fine, but then I ran into a problem. And so the idea here is that you have this audio buffer list, and then there's an array of audio buffers on it there, which are also themselves structs. However, when you try to assign that, it doesn't work. And the reason this doesn't work is because I was trying to use an array of audio buffers, and the way that this C struct maps over into Swift is actually as a tuple. So, whereas an NS array maps over and you get a nice regular Swift array of the appropriate type, regular C-style arrays do not. They actually map over as tuples, which are of a fixed size, as in they don't grow at all. And in this particular case, a one tuple is actually equivalent to just a single object. So once you understand that, it's pretty obvious, okay, this is just like a buffer. Obviously, I can't assign an array of them to it. So, I kind of banged my head on this for a while, did some Stack Overflowing, and eventually I came across a suggested solution and also some naming for this particular pattern here. So this is called Flexible Array Member, and this became an official part of C in C99, which I'm pretty sure was 1999. Prior to that, it was known as the struct hack. The reasons for which will become apparent shortly. So the general idea here is you have a struct, and it's sort of divided into two parts. The first part has a fixed size set of struct members, and then you have what is basically a dynamic array as the last element that you can grow as needed. So that you actually know how big that array is, one of the preceding struct members has to be a count value so that you can use that to size everything else. Whenever you're dealing with these, you have to create them with malloc, and you have to pass pointers around. If you try to assign it to a non-pointer, like just a struct value, like you just got rid of everything else, and if you index into that, you're going to be reading random memory, which probably won't end well. And there's also some alignment issues, which largely you don't have to deal with, I think. All right. So here's our friendly struct, the audio buffer list. And what's kind of funny is if you actually only have one, you can just use it as a normal struct. So this you can happily create in C and in Swift, and no problems there. The problem comes when you have one that's bigger. So now the problem is that your type definition of audio buffer list is actually lying, because the memory that it's pointing to does not have a single element array, it has a multiple element array. And this is what makes it so confusing. If you were going to do this in Objective-C, it's really not that bad. There's some handy macros to help you figure out the size of it. So the first thing you need to know is the size of the static sort of fixed sized portion of the struct, and you can do that with this offset of macro. This does not actually exist in Swift. We'll get to that later. So you say offset of, and then you give it a struct member, and you get back the offset of that particular struct member from the beginning of the struct, which is also equivalent to all of that sizing plus the additional padding for memory alignment and all that good stuff. So you take that part, and then just the size of the child structs times however many of them there are, and that's your actual size. So malloc that up, and you're good to go. Once you've done that, using them is pretty simple. This is kind of the funny part. So normally when you have a single element array and you access the second element, that's a bug, but here you're doing it on purpose. Thus the struct hack. But from a code perspective, you don't really have to treat it any differently from that point. You just have to remember to always pass it around as a pointer and free it, of course, when you're done. So not that big of a deal. But how do you do this in Swift, which is supposed to be type safe and like not allow you to do evil things to yourself like this? As a side note, I'm really curious. I haven't tried this yet. I've been doing all this stuff in Xcode 6.4, Swift 1.2, so I haven't yet used the address sanitizer, but I'm imagining that that probably wouldn't play so well with this stuff. So if anyone has a chance to try this in Xcode 7, I'd like to hear how it went for you. Okay, so Swift has various pointer types in it, and I'm only going to talk about specifically the ones that you need to do this. So the first one is unsafe mutable pointer, which is basically equal to just a regular old pointer in C. The thing that's weird about this is it's designed for use with just one type, but in our case, because our type actually lies about the size of the object underneath, we can't use it directly. So if in order to allocate the proper amount of memory, the first thing you need to do is create something in a known size. So what I decided to use was uint8, just because I know that's a byte, and I also saw it referenced in some Stack Overflow stuff, and it worked in my testing. So it could probably be something else. You could probably use an int or char or whatever. We're going to use uint8. So the first thing you have to do is figure out how much memory you need to allocate, and then you create one of these pointers, and then to do anything useful with it, you now have to create a second pointer that actually does reference the audio buffer list, and that'll handle the offsets and all that stuff for you. And that looks something like this. Also, just to make it more fun, size of in Swift is not the same as size of in C. So in C, size of gives you the size of a type or a value, including the any padding necessary for memory alignment. In Swift, it just gives you the size with no alignment at all. So instead, you have to use stride of. Definitely useful to know. So we have our buffers. We do stride of buffer list plus the number of buffers times the actual stride of the buffers. And then you just call the unsafe mutable pointer alloc on it, and now you have some memory. I'm not 100% sure that this isn't going to like over allocate a little bit of memory, but it in all of my testing worked just fine. So I think worst case you may end up with like a little bit extra that you don't actually need, but you should have it at least enough. So it shouldn't create any problems, but if you're being like hyper pedantic about it, maybe an issue. Okay, once you do this, you have your buffer list pointer, and with that you can now assign, this is the number of buffers, this was that first part, so this is the fixed length portion of the struct, so you can just do direct assignment with that like you would normally. That still doesn't solve the whole thing of a tuple not being able to take an array. So for that we have our good friend memcopy. Yeah, I think I laughed out loud for about 5 minutes when I saw this and that it worked. I'm like, so I'm using memcopy in Swift. Okay. So this works. I couldn't actually find documentation on this, but structs that are defined in C are supposed to be guaranteed to retain the same memory layout in Swift. The same is not true for Swift objects. Of course, if you're dealing with Swift objects, you don't have to deal with this nonsense, so it shouldn't really be a problem. But it is a little weird in that way. But basically, all you need to do is just use the little, address of operator there with your array of structs, and you can copy them right on into the fam struct. And that works. However, that has some problems. Like you can't actually read from it. So if you wanted to, for example, write unit tests for your code, good luck with that, unless you want your like assertions to have their own little version of memcopy in them, which does not sound fun. And it's kind of awkward. Like, who wants to deal with that? Fortunately, there is a way around this. So first off, I think if you're going to do something like this, you should probably stick it in a wrapper of some kind, just so that it's reusable. The added bonus here too is if you decide to use an object, you can use the dinit method to handle deallocation of the memory, so you no longer have to deal explicitly with the memory management. So you get a couple wins there right off the bat. Still doesn't directly address the assignment of an array into the variable part of the fam, though. For that, we need our friend unsafe mutable buffer pointer. So this pointer type isn't for allocating memory, it just basically points to it. So what we want to do with this one is we still have our initial uint8 pointer that we use to allocate all of the memory. Then the second pointer that we created that points to the audio buffer lists, we use that one to determine the offsets for things. And then we create this new one that will point at the first element of the variable portion of the struct. All right. Okay, I thought I had a better picture, but maybe that's later. So here we go. We can create that. And it's, just need a property so that you can refer to it later, and then it's just a normal assignment. The first argument is simply the address of where the buffer's member starts, and just the count. So it's pretty easy. You really can't get it wrong. So it makes me feel a lot more comfortable than the memcopy approach. Okay, now we still have a problem with that in that we can't actually write to that memory yet because it's just all still inside of our wrapper. So to make that a little bit easier, we can make our wrapper adopt the mutable collection type. So to satisfy that, you just have to give it a starting and an ending index, which is always going to be 0, always going to be the size of the variable length array. You have to provide a generator function, which these things still mess me up a lot. However, in this case, it's really easy because this is an index collection. You just return an indexing generator and you're done. That's it. And then to actually handle reading and writing from the buffers, you just delegate to the buffer pointer that we created in the last step. Also very easy. And here it is in action. So once you have this, you just create your wrapper, give it a count. You can directly assign your little child structs and read them. And if you need to pass that pointer to some C function, you can do that too. So works pretty well. So after I went all through this, turns out that Apple did this for us in some places. But not everywhere. So, the one that I ran into this problem with was actually an audio file marker list, and for that one there is no Apple provided wrappers, so it wasn't an option there. This one also works a little bit differently. They implemented it as a struct, so you still have to deal with the memory management yourself. You can't leverage the dinit on objects, which, I don't know, maybe that works for you, just whatever is appropriate for your use case. But one thing that theirs does do that mine doesn't, so in Core Audio, a lot of these structs, sometimes you create objects and pass them to other things, but sometimes you create callbacks and they get past the pointer. So my version wouldn't actually handle that, but this one does. If you see that initializer there, if you were to write a callback function, then inside of that function you could take the pointer that the framework gave you, pass it into this wrapper, and then now you would be able to use all the swiftiness to deal with that data. So that's another pro there. If you want to look at this more closely, it's like next to impossible to find these things in Xcode sometimes. Like, as far as I can tell, all the Swift headers are like dynamically generated. And if you look at the ones for Core Audio, they're not in there, but then you can like click into another one and then you get this nice one that actually has all the stuff you care about. I put a copy of that online, so you can go read it. It's commented. I couldn't fit it on the slide with the comments. Okay, so here are some recommendations. Personally, I don't like the memcopy approach. It does work, as far as I can tell. So if you just need to do something simple, or it's not something you're actually shipping, like maybe that's okay. But you can only write to it. You can't read from it. You're also coupling yourself. Like, I don't really like the idea of creating a Swift array with structs in it and passing it in. Like, that worked in my testing, but I couldn't find any documentation. Plus, if any of that stuff ever changes, you're gonna have to deal with it. So it's really not future-proof. Doing this stuff, like, once you learn how to use the underlying frameworks, just doing it in C or Objective-C is not really that bad. So for like the thing that I was working on, I just did it in Objective-C, and I'm happy with that. However, and I don't know, like, the trouble of writing the wrappers and making sure they work right and all that, like, you really need to have some, I think you need to justify that work for maintaining it. So if you're like heavily using these APIs, then okay, it probably makes sense at that point. Or maybe depending upon your team composition, like, you may have people that aren't really comfortable with C. So this would sort of make it more accessible to a larger audience. I looked through some of the various iOS frameworks, and these were the only ones that I found that contained these kinds of structs. So if you don't recognize any of those, you can probably just forget everything that I just told you and never deal with it. Yeah, that's pretty much it. This is me. Like I said, the talk's online if you want to go check it out. Any questions?
I was wondering, Mark, did you have a chance to look at enough of Apple's wrappers? And maybe there just aren't enough of these that it would matter, but I was wondering if there's like a mechanical translation, like we could expect Apple just to eventually automatically bridge this sort of thing?
That's what I'm hoping for, and I've attempted to open a radar like 5 times. I haven't been able to explain it clearly enough that I was happy with it. I guess, like, where I started, like all the way at the beginning, I mean, it would be great if that just worked. But it doesn't. So I don't know. And I mean, I guess it is like, it's not an NS array, it's a C array, and even in Objective-C, those are kind of a pain to deal with. So like, they haven't made it easier there. I don't know. I did try to do like a generic version. I thought that would be cool. Like, oh, let's do generics and like, generic Swift or Reified, so you have this stuff at runtime, it would work. But I couldn't get it to work, and I didn't have a confident enough grasp of the memory alignment issues that I was comfortable with anything that I could think of.
The error messages are a lot better in Swift 2 than Xcode.
I have read that, and I'm really looking forward to this. All this stuff I did, I'm still in 6.4 at this point. So yeah, looking forward to that and a lot of those new features.
It'll be interesting to see how many things that you're doing broke in 2.0.
So back in the couple first releases, I did try it, and it was still working at that point. But I stopped checking eventually because trying to keep up with both of them was just kind of too much work.
And I would encourage you to always file a radar,
Okay.
even if you're having a hard time finding the right words.
Yeah.
Especially with Swift, the team is very keen.
They are, and they're active in the forums too. Like some of the stride of size of things, I found that in the forums from an Apple engineer. Now that I've prepared this, I feel like I could actually write one that made sense. So I do plan on doing it. It's just haven't gotten to it yet. Yeah.
Can we assume that C structs basically don't work in Swift?
So they work if you just use them alone. The problem is that this flexible array member hacky thing, that's really where it breaks down.
So if I just have a struct in C, I can translate that into Swift.
That'll come in for you.
I'll be okay.
Yeah, if you just have a regular struct, you're fine. It's just when you're
scaring me.
okay. Yeah, this is definitely an edge case. And like that list at the end, like those are really the only frameworks that even use these, so it's pretty rare. But I thought it was really interesting, like with Swift, the stated goal being they want to like do everything from high level scripting all the way down to like OS level programming. So like those kind of boundary things. I don't know. This is just one of those. I thought it was kind of fascinating.
You would love doing Swift with 132. 132 has a lot of APIs. They make that look tame. But I mean, I know because I just got done with the contract at Microsoft doing 132 SDKs, escalation engineer stuff. So
So audio stuff I find interesting. Low-level Windows stuff, not so much.
yeah, it's not just the number of elements of the array; it's that each one of the strings is flexible in length.
Hmm.
Too, above and beyond the fact that there's. So yes, recursive variable length.
Okay. Cool. All right. Thank you.